If you Google search the most beautiful math equation in the world, you're going to get this kind of like crazy result that's a relationship between like E and there's an I and a pi and the I is up in the power. I love it. I mean, it's just so beautiful and perfect and surprising and counterintuitive. And I'm going to present the proof here that is really like the traditional way to see this, which uses Taylor's theorem. And there's a lot of other things to say about this. There's other ways that you could have seen this coming, and also there's other ways that you can look at this result and reinterpret our understanding of imaginary numbers. But I don't have time for all of that in this video. So let me know if you're interested in some of the other fallout and topics surrounding this. Let me know, and maybe I can make some follow-up videos about it. Here is Leonhard Euler. I guess you say Euler. So he is an amazing figure in the history of math, according to Laplace. Read Euler. He is the master of us all. And according to Gauss, the study of Euler's works will remain the best school for the different fields of mathematics, and nothing else can replace it. He is considered the most prolific mathematician of all time with 850 publications. And so some of the like just sort of everyday influences he introduced using pi, or I guess popularized to 3.14 is pi, the f of x notation, capital sigma for summation notation, and also the letter I to express the imaginary unit, which is what, and we're going to explore the fallout of that definition in this video. And it starts with this just kind of fun exploration. What happens if you just start doing I to a bunch of powers? It's cool. There's kind of a pattern that falls out of this. So let's start with I to the power of 0. Okay, so I to the power of 0 is 1. Okay, duh. All right, I to the power of I, that's even more duh. That's just I. Okay, now I squared, all right, the definition is that's -1. All right, now what are we going to do? What are we going to do with I cubed here? Okay, so I cubed, that is really I squared times I. So all I'm doing is I'm just peeling off I squared because I know what to do with I squared. So that's going to be -1 times I. Okay, so you get -I there. All right, now what about I to the 4th? All right, so I'm going to try the same trick here. Let me just peel off I squared. So I'm going to have I squared times I squared. All right, I think we're getting somewhere now. So there's going to be -1 times -1, so we're going to get +1. All right, now what happens when you get to I to the 5th? All right, so when we do I to the 4th, we get 1, and now the pattern is just going to repeat, right? Because I to the 5th, I can pull off the first 4 of them, and I'm going to have I to the 4th times another value of I, and I to the 4th is 1, so this whole thing is just going to be 1 times I, so we get I again. Now I to the 6th, what that's going to be? That's going to be I to the 4th times I squared, so that's going to give me -1. So you can see we've got this pattern, 1 I, -1, -I, 1 I, -1, -I, 1 I, -1, -I. All right, let me write that down. So here's the result. All the powers of I are going to come in little chunks, and those blocks are going to be blocks of size 4. You can see them every 4 numbers. It just repeats here. 1 I, -1, -I, 1 I, -1, -I. Okay, so what I want to do next is I actually see things that are alternating, and I see that some of them are real numbers and some of them are imaginary numbers. So if I just go through and I just circle all the even powers, you see I to the 0, I squared, I to the 4th, I to the 6th, I to the 8th, here's 10, 12, 14. You can just see this pattern just goes 1, -1, 1, -1, 1, -1, 1, -1. Okay, so look at the missing pieces there and see what the pattern for the odds are. The odd powers are always just going to be I, -I, I, -I, I, -I. Okay, so sweet. Let me separate out the even powers and the odd power. Okay, so let me just separate these. Here I've got all the even powers are going to go right there. And then all the odd powers, I'm going to separate them down here. you can see that, so I started off with I to the power of k, and now I've split that up into all of the k's that are of the form 2 times n, and all of the k's that are of the form 2 times n plus 1. That's just how we write even and odd numbers. Okay, so now this formula is just -1 to the n. That's it, right? It's just alternating powers of 1 and -1, and n here starts at 0, and that will give us, when I plug 0 into 2 to the n, I will get 0. And then for the odd powers, I'm just going to have -1 to the n times I. And that's going to perfectly generate this sequence of plus I minus I. And you can see if I plug in n equals 0, I am going to get the first power of I, and that is going to give me that number right there. So brilliant. We've really got it here. We've got a formula, and some of you may be already able to see the end game of this, what's going to happen when I plug this into Taylor series, because here I have a formula that's going to give me the powers of I based on the odd terms and the even terms. So let's bring Taylor's theorem into this, and then we really should be able to just see Euler's identity immediately. Taylor's theorem is a way to turn functions into power series. And the process involves just taking a bunch of derivatives and plugging in a point and then putting that over n factorial. And so long as you're inside the radius of convergence, then this power series is going to give you the same answer as evaluating that function. And if you haven't done this before, for e to the x and sine and cosine, I encourage you to do it. Basically what you're going to get is e to the x and cosine and sine are going to give you these power series expansions, the Taylor series expansions. Sometimes people call them Maclaurin series expansions. There's a lot of fancy names. I'm just named after people. You can see here that the cosine is all a bunch of even powers and the sine is all a bunch of odd powers. So it's probably coming together for you already. So what I'm going to do is I'm going to take this formula for e to the x and I'm going to plug in ix in for the powers of x, and this is what you get. So I mean, just the meaning of these symbols right here is just like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc., etc. And all I've done is I've plugged in I. And so you can see here I have an I to the power of 0. Here I have an I to the power of 1. Here I have an I to the power of 2. Here I have an I to the power of 3. Here I have an I to the power of 4. Okay. So we got this kind of monstrous power series written out here. So what I'm going to do next is plug in this rule for the powers of I. So I'm going to separate them into odds and evens and then simplify these powers of I. And what should fall out is some combination of sines and cosines. It's fantastic. Let's see how that goes. Okay, what I'm going to do is I am just going to take all of these odd powers, I've grabbed them, and I'm just going to separate out all of these odd powers and the even powers. Now, what's going to happen to these i's? Okay, all of these i's are all just the even powers of I all next to the even powers of x. So that means that just the even powers here are going to be the sum of, so this I to a bunch of even powers, according to this rule up here, is just going to be -1 to the n, and then all of my x, oh, I forgot my little negative, -1 to the n, and then a bunch of x's to even powers divided by a bunch of even factorials, right? Okay, now where does it start? This starts at 0, so I'm going to put n equals 0 up to 100. And what about the odd powers? So the odd powers are going to have the sum of, I'm going to scoot them over a little bit, the sum of, okay, so what have I got here? According to this, when you do odd powers of I, you should have -1 to the n. Now I'm going to take this little factor of I and I'm going to put it out front. And then I'm going to have x to the power of 2n plus 1. Oh, I'm almost falling off the page. Over 2n plus 1 factorial. Okay, so I have taken e to the x and I have broken it up into a bunch of even powers and a bunch of odd powers, and these are the series that I came up with. And look, there it is right there, the series for sines and cosines. So this is fantastic. Let me just write down what the conclusion is. What a fantastic result. This really completely changes the way that we can think about imaginary numbers and what it means to have an imaginary number up in the exponent. And just to recap here, what happened is I plugged ix, literally just straight go away thing. I literally just straight substituted I to the x into this Taylor series. And I applied this rule for powers, and that just gave me the Taylor series for sine and cosine, and the sine had a little I in front of him. So, I just wrote down that result. What that means, I mean, this is just because the formulas are the same, these two things must be equal to each other. So this is really a head scratcher, and there's a lot of fallout for what this means, but, math theory is pointless without at least some basic examples. So let me just write down some basic examples of some kind of wild results that you can get from applying this theorem. The most obvious application of this equation is to just literally plug in a number. So let's see, here I want to evaluate e to the power of I pi. So according to Euler's formula, this is just going to be the cosine of pi plus I times the sine of pi. Too many parentheses, I times the sine of pi. Okay, so the cosine of pi is -1. And I times the sine of pi is 0. So this is -1 plus 0i. So this conclusion here is that e to the power of I pi is equal to -1. Whoa, this is fantastic. One of the reasons that this equation is so beautiful is because it has all of the important constants in it, right? It has e, I, pi, and -1 in it. So I mean, that is just fantastic. And I'm not joking, okay? If you just Google search the most beautiful equation in math, it does actually give you Euler's identity here. E to the I pi plus 1 is equal to 0. And there's lots of content on this if you want to check it out. And then the other thing I want to bring up is that, I'm not just making this up, okay? Okay, the calculator 100% agrees with me. E to the I pi is -1. And actually this other one here, if I do, I just want you to see how to push these buttons. You can do this too, right? So e to the power of I, that second period, and then pi divided by 2. This should give me I, because this is the cosine of pi over 2, which is 0, right? Cosine pi over 2. Cos pi over 2, that's 0. Plus I sine pi over 2. Sine pi over 2 is 1. So here you just get I. So there's a few really awesome applications of this. I mean, it's just crazy that this answer just comes out this way and that it's right. And I want to give you just a few head scratchers because this rabbit hole goes deeper than just these few little examples. I wouldn't be a good math teacher if I didn't give you something to think about. So one is, I want you to try to imagine solving this equation. I mean, obviously, one of the solutions is x is equal to 1, but maybe there could be more solutions. So here's my hint for this one. If you plug in this formula, if x is going to be e to the I theta, then this equation can be e to the I theta cubed is equal to 1. So really 1 is really 1 plus 0i. So what angles could I do where I get this is supposed to be the cosine and that's supposed to be the sine. So what angles could you do that give you cosine of 1 and sine of 0? So this could be e to the power of 2 pi k times I. Ooh, that's interesting. I think if you look right here, you may be able to solve that equation for theta. This is really interesting. If you're interested in this, the name of this topic is called the roots of unity. And if you want to, let me know. I'll make a whole video on the roots of unity. It's really fantastic content. Okay, now for this one right here, this is really fun because if you take this to a math tutor, they're going to tell you it's not possible, right? Because the cosine of x is always going to give you a number between 0 and 1, but that's not true. In fact, there are imaginary numbers that solve this equation. So it's pretty fantastic. Let's check this out. So what we know is that e to the ix is equal to cos x plus I sine x. So what I'm going to do here is I'm going to plug in negative ix. So this is going to be cos negative x plus I sine negative x. And now remember, cosine is all the even powers, so it's an even function, and sine is all the odd powers, so it's an odd function. So all these even powers are going to just cancel that negative right there. Now all the odd powers, I can factor the negative one out front. So this is going to be negative I sine x. Okay, so what's going to happen if I add this equation right there and that equation right there? Can you see those signs are going to cancel right there? So e to the ix, that's this one, plus e to the negative ix, that's this one. When you add them together, those signs are going to cancel, and I'm going to have 2 cosines. So I just get 2 cos x. So if I divide both sides by 2, I'm going to just divide both sides by 2 here. I get e to the ix plus e to the negative ix is equal to cos x. So what you can do is you can take this and substitute it into that equation right there, and that can actually give you a way to solve for x, and you're going to end up with some imaginary numbers. So when they tell you that the cosine of x can never be equal to 2, it's not true. So I'm really interested to see if you can make some progress, if these hints are enough. So this is really a fun topic. It's one of my favorite things. I hope you enjoyed it. You know, if you have any questions, let me know, and I'll see if I'll do my best to answer them.